Welcome back, Physical Science 20. This is section 4.2, Synthesis and Decomposition Reactions. So I want to look at this booklet, we'll go through it, and you'll see what questions to do at the end of it. So we're going to highlight some things, add some things, and hopefully this will all make sense after we do a few practice questions as well. So here it's just introduction, talking about the periodic table. Elements are predictable, the properties, because of how they're arranged. And then they give this little demo here with reacting alkali metals with chlorine, etc. Sodium and chlorine gas yields sodium chloride. So we have two elements coming together to make a compound. Here we have potassium, which is in the same group as sodium. And it's a somewhat similar reaction, except a little more vigorous. First thing though, diatomic elements. If you look at this section right here, if you could write this in, it's kind of like a little phonetic word here to illustrate which elements, when they exist by themselves, are actually diatomic. So Hofbrinkel, in my room here I have a picture of a clown here that has this name illustrated. Basically that group on the right hand side of the periodic table, hydrogen, which is actually on the left, so it's the only one that's on the left, OFBRINCl actually exists as H2, N2, O2, etc. So whenever you have a question that involves, let's say, hydrogen, they're talking about H2. So just be aware of that, because I know some of you had issues with that when you were doing some of the questions from the previous section. Okay. We could use this pattern to predict the products of other reactions involving metal and chlorine. Magnesium, for example, also reacts with chlorine. The product of this reaction is the compound magnesium chloride. Magnesium has an ionic charge of +2, as you see from your pink periodic tables. So the chemical formula is MgCl2. Chloride, the chloride ion is negative. So you can see individually the metals or the diatomic gases here exist like that, but when they come together to form a compound, that's when you have to look at the charges on your pink periodic tables. So Mg is 2+, Cl is -1, so of course we need two chlorides to make the compound magnesium chloride. And of course then after that we have to balance it, but guess what, it's already balanced since chlorine is one of these diatomics and is Cl2. Of course, there are millions of known reactions. Chemists group them into patterns to organize them. Grouping reactions also makes the prediction of reaction products much simpler. In the next few sections, you learn how to recognize 4 patterns that chemists use to identify chemical reactions. Note, however, there are many ways in which reactions can be classified. Using the patterns is just one way. So this booklet deals with synthesis and decomposition ones. The next booklet will deal with single displacement, and the next one double replacement or double displacement. And then lastly, we'll look at combustion reactions. So synthesis reactions have this form, A plus B making AB. So we think of element A and element B coming together to form compound AB. So two reactants combine to form one larger or more complex product. For this to occur, the reactants must first collide, break existing bonds between atoms, and form new bonds. The chemical equation is seen here. So this is the general form of it. And you can use this pattern to predict synthesis reactions. So for example here, magnesium combined with oxygen, and note oxygen is one of those Hofbrinkel elements, so that's why it's O2. So it follows the form A plus B gives AB, or Mg plus O2 gives, well, magnesium and oxide. And of course if we look at our list of charges here, magnesium is 2+, oxide is 2-, so they're both 2+, 2-, so they come together in a 1-to-1 ratio, MgO. And of course to balance that out, we would have to have, let's say I have 1 magnesium, that's good, 2 oxygen, 1 oxygen, so I have to place a 2 in front of the MgO. That'll also give me 2 Mgs, so I have to put a 2 Mg in front of there. See if you can do these practice questions just over to the right here. Maybe pause the video and see if you can make these synthesis reactions when calcium and bromine combine together and aluminum and oxygen. So maybe pause the video and see if you can do that. Okay, if you had a chance to do that, calcium and bromine is one of those Hofbrinkel elements, so it exists as Br2. And calcium and bromine, if we look here, calcium 2 plus, bromine, or bromide, sorry, -1. So I need to have 2 bromides for every 1 calcium to balance it out. And of course, because this is a Hofbrink element, it's already balanced. Aluminum and oxygen. Aluminum is just Al. Oxygen is a Hofbrink element, so it's O2. And if we look at aluminum and oxide, aluminum is 3 plus, oxide is 2 negative, right here. So 3 and 2, the lowest common multiple is 6. So if aluminum's worth 3 plus, if I have 2 of them, that's 6 positives. If oxide is 2 negative, I need 3 of them to make 6 negative. So Al2O3 is the formula for aluminum oxide. So if we take a look here, I have 2 aluminum. So if I put a 2 in front of here, we'll see that I'll have an uneven amount of oxides. And you can see here O2, O3, lowest common multiple is 6. So I've put a 3 in front of here, I have 6 oxygens on the left. Put a 2 over here, 6 oxygens on the right. That makes a total of 4 aluminums, so I need 4 aluminums on the right, or on the left, sorry. Okay, so those are examples that involve metals and non-metals coming together. What about if we just have non-metals coming together? So for these will form molecular compounds. So we could have that. Also, synthesis reactions involving hydrogen. Hydrogen is a group 1 element. Most group 1 elements form ionic compounds when they bond together. Hydrogen, however, usually forms molecular compounds. Molecular compounds are made up of atoms, not ions. However, ionic charges are still useful in predicting the products of synthesis reactions involving hydrogen. So for example, the reaction between hydrogen and chlorine makes hydrochloric acid. So hydrogen and chlorine are both Hofbrinkels, so H2 and Cl2. And when they come together, if I look at charges, hydrogen's +1, chloride's -1, so they come together in a 1-to-1 ratio. So I get HCl, but of course I need 2 and 2, so put a 2 in front of the HCl, and it becomes hydrochloric acid, like that. The reaction between hydrogen and oxygen follows the pattern of synthesis, like the other ones. A plus B gives you AB. If the ionic charges of hydrogen and oxygen are applied, we can see that 2 hydrogen atoms are needed to balance the ionic charge of 1 oxygen. So like H2O, the product would be H2O, therefore the balance equation would be a little bit different. So you can see here I have to have 2 oxygens here, so I need a 2 here to make 2 oxygens. That gives me 4 hydrogens, if I put that 2 in front. The reaction of hydrogen with oxygen releases a great deal of energy as well as water. The reaction has the potential to be an important source of green energy because we're dealing with hydrogen gas, oxygen gas, water vapor, very clean energy source, and what's given off is not harmful either. In fact, a fleet of hydrogen buses was used in Vancouver during the 2010 Winter Olympics, as seen here. However, since hydrogen does not occur naturally as an element, it has to be extracted from compounds that contain hydrogen. This, of course, requires energy. Therefore, hydrogen fuel can be considered green only if it is generated from environmentally friendly raw materials, using renewable energy sources. Water would be suitable raw material, solar power would be another suitable power. Now, if you look here, I highlight things in green throughout, because later on in the course you have to do a research project or a lab. So if you wish to research more on using hydrogen as fuel, you certainly could. So I'm just outlining this here to joggle your memory when the time comes that you could do that as a potential idea when you look at something, one of the parts of the course in more detail or research something. Okay. Synthesis reactions not involving hydrogen. The products of synthesis reactions of non-metals other than hydrogen are difficult to predict at times. The products of these reactions are often depend upon the reaction conditions. For example, 2 products are possible when carbon and oxygen combine. So carbon and oxygen can either make carbon dioxide or carbon and oxygen can make carbon monoxide. So to figure out which one we would get, we'd have to conduct some chemical tests to see if the gas is carbon dioxide or carbon monoxide. So some of these are somewhat difficult to predict because there are more conditions that are addressed there. Okay, I think I will stop there. I think we have about 10 minutes into the video, so we'll look at part 2 in a bit. See you soon.